Welcome, dear listener, to a question that seems simple until you hold it up to the light. On the scale of everyday life, time has a clear direction. Warm things cool, mixed things stay mixed. Memories point toward what has already happened. Yet many of the fundamental equations we use to describe the world do not care about this direction. If you flip the sign of time in Newton's equations, the trajectories remain valid. If you reverse time in the Schrödinger equation, the evolution is just as lawful, provided you also reverse complex phases appropriately. Even Maxwell's equations, when written in a form that treats electric and magnetic fields symmetrically, allow solutions that run backward as cleanly as forward. There is a stark contrast between microscopic time reversal symmetry and the macroscopic arrow we experience. Why is backwards so rare that we never see it? Imagine a dream in which the microscopic details are perfectly known. Every molecule in a cup of tea is tracked. Every collision is cataloged. If you reverse all the molecular velocities at a single instant, the cup would, in principle, return to its warmer state as energy flows back from the air into the liquid. This is not fantasy in the equations, it is a lawful solution of classical mechanics. But the practical demands are merciless. You would need to measure and reverse the state of roughly 10 raised to the power of 23 degrees of freedom with exquisite precision, down to tiny correlations that diffuse into the room and into the walls and into the night beyond the window. A single thermal photon leaving the window carries away information you would have to retrieve to make the reversal exact. The dream reveals the core of the problem. The equations allow reversal. The bookkeeping of information and the combinatorics of possibilities do not. Physicists learn to formalize this tension in several ways. One pathway is statistical mechanics, which treats the microscopic state space as a vast collection of possibilities and uses probability to speak about typical behavior. In that language, entropy is a measure of how many microstates correspond to the macroscopic features you can actually see. A tepid, well-mixed room can be realized by enormously many microstates. A room in which a sharp pulse of heat remains bunched in one corner can be realized by comparatively few. The thermodynamic arrow is the tendency for macrostates to drift toward those that can be realized in more ways. It is not a prohibition against the reverse. It is a statement about overwhelming likelihoods when the number of constituents is astronomical. Boltzmann framed this in a way that is still helpful. How many hidden microstates lie behind a single calm macrostate? If you slice the microscopic phase space into coarse cells, finite boxes that reflect the limited resolution of macroscopic observation, the coarse-grained entropy tends to rise because the fine dynamics stretch and fold the distribution into structures too thin for your coarse boxes to resolve. Liouville's theorem guarantees that the fine-grained phase space volume is preserved. Nothing in the exact dynamics creates or destroys volume. But once you accept coarse graining, once you accept that you do not track every correlation to arbitrary precision, the mixing of trajectories makes the coarse-grained description lose information. The entropy that increases in the second law is the coarse-grained entropy. The rise is a statement about what happens to the information you fail to follow. If microscopic laws allow reversal, why don't we see cups unshatter? The microscopic dynamics are time reversal invariant. Then for any entropy-increasing evolution, you can construct a time-reversed evolution in which entropy would seem to decrease. Boltzmann's answer is not to deny the possibility, it is to point out its practical measure. Those decreasing entropy trajectories are real, but exceptionally rare in the distribution compatible with ordinary macroscopic reparation. You can, in principle, prepare them In practice, any small error destroys them. This is where sensitive dependence on initial conditions becomes a physical limit and not merely a mathematical curiosity. The tiniest drift in a single component, one atom scattered a little differently, one photon lost, propagates outward and ruins the delicate correlations that decreasing entropy trajectories require. It helps to distinguish between exact reversibility and engineered unwinding. Exact reversibility would require setting the system's microstate to the precise time-reversed configuration. Engineered unwinding is different. You design an evolution that cancels the spreading of a particular kind of motion without claiming to reverse the entire world. A time reversal mirror records a complicated wave field and re-emits the time-reversed signal so that the field refocuses to its source. What would it take to make a wave walk backward through an entire world, not just a single room? The walls, the air, and the microphones are not run backward. Only the wave pattern is. Phase conjugation plays a similar role. A special medium generates a new wave that is the complex conjugate of the incoming field, and that wave retraces the distorted path back through a scattering medium. Hahn echo shows how a dephasing ensemble of spins can be made to rephase if you apply a well-timed pi pulse that flips their phases. The macroscopic signal returns as if the spin evolution had been unwound. If a small echo is possible, how far could we scale that memory before the world writes over it? These are controlled, local reversals. The effect is real, but the scope is modest. If a self is a living process, what would it mean to gently rewind it? From the quantum perspective, time reversal needs care because it is represented not by an ordinary unitary operator, but by an anti-unitary one. When you perform the time reversal operation, you reverse momenta and spin directions and take the complex conjugate of amplitudes. In most interactions, the equations are invariant under that transformation. There are exceptions in the weak interaction. Certain processes involving kaons and B mesons show a genuine microscopic preference for one temporal direction, a violation of T symmetry linked by the CPT theorem to violations of CP symmetry. These effects exist and are measured, but their scale is far too small to explain the thermodynamic arrow we live with. For that arrow, the key is not a small fundamental asymmetry. The key is the special initial condition of our observable universe and the amplification of typicality in systems with huge numbers of degrees of freedom. There are precise ways to describe typicality. The concept of detailed balance in Markov processes captures how, near equilibrium, microscopic transitions tend to occur with probabilities that ensure no net macroscopic flow. When detailed balance holds, there is no arrow. Drive the system slightly away from equilibrium, and you can write fluctuation theorems that quantify how likely it is to observe short-lived entropy-decreasing excursions. The Jarzynski equality and Crookes fluctuation theorem are two such results. They tell you that even when average entropy production is positive, the distribution of microscopic work values includes rare negative fluctuations weighted in a way that preserves exact identities. These theorems do not blunt the second law, they sharpen it by showing how it emerges statistically from time-symmetric equations. Information theory lets you say this in yet another way. To reverse a process, you need to preserve the information that the forward dynamics would otherwise disperse into microscopic degrees of freedom. Maxwell's conceptual daemon tries to exploit information to sort molecules and reduce entropy. But to function, it must acquire and eventually erase information. Landauer's principle connects the erasure of information to heat dissipation. This is enough to reestablish the second law when the daemon is included in the bookkeeping. Any scheme to reverse macroscopic time has to pay these costs somewhere. And in practice, the payment overwhelms the local gain. There are also mathematical certainties that are beautiful but not practically helpful. In a closed, bounded Hamiltonian system, the Poincaré recurrence theorem guarantees that the system state will return arbitrarily close to its initial configuration after a sufficiently long time. If you imagine sealing a gas in a perfectly isolated box and waiting long enough, the gas will, with probability 1, explore the phase space in such a way that it comes near its starting arrangement. The catch is in the time scale. For macroscopic systems, recurrence times are so enormous that they make the age of the universe look small. The theorem is true, but it does not offer a feasible path to reversal. It only confirms that the microscopic dynamics retain the information in principle, hidden in correlations spread across an immense space. One can make all of this less abstract by examining concrete experiments that edge as close as possible to reversal. In nuclear magnetic resonance, a Loschmidt echo experiment takes a system that evolves under one Hamiltonian for some time and then evolves under the approximate negative of that Hamiltonian. If the engineering is good, the state refocuses, and a measure of fidelity quantifies how closely it returns. Any imperfection, mismatch of fields, uncontrolled couplings, small environmental interactions, reduces the echo. The rate at which the echo decays becomes a measure of the system's sensitivity to perturbations, a bridge between the clean reversibility of the equations and the practical irreversibility of the lab. Even in classical wave physics, the success of time reversal mirrors depends on how thoroughly you capture and re-emit the field. If your microphones miss some part of the wavefront or your speakers re-emit imperfectly, the refocusing loses sharpness. The unmeasured pieces act like an environment. They carry away correlations that your re-emitted signal cannot reclaim. In optics, phase conjugate mirrors work best when the nonlinear medium captures the full transverse structure of the beam and when losses are minimal. Losses do not just reduce intensity, they erase phase relationships that encode the path information. The common theme is that reversal requires keeping track of phase space structure with accuracy that narrows as the system grows. When people speak about reversing the flow of time for heat, they often mean reversing diffusion. Diffusion is a paradigmatic, irreversible process in which a concentration gradient relaxes to uniformity. The diffusion equation itself is not time reversal invariant. If you change T to negative T, you get anti-diffusion, which takes smooth profiles and amplifies small fluctuations into sharp, unphysical spikes. But the diffusion equation is a coarse-grained description that emerges from many small random steps. If you model the underlying microscopic dynamics as elastic collisions among particles that conserve energy and momentum, you can write equations that are time reversal invariant. The irreversibility of diffusion arises from ignoring degrees of freedom, the exact collision histories, that you cannot or choose not to track. Reversal would require reconstructing those histories sufficiently to drive the system along the anti-diffusive path without triggering instabilities. A related distinction helps avoid confusion. Microscopic reversibility is the property that transition probabilities for a sequence of microstates and the reverse sequence are related in a way that reflects time reversal symmetry. Macroscopic irreversibility is the observation that, with overwhelmingly high probability, macroscopic variables follow trajectories that move toward equilibrium. The first does not negate the second, it underwrites it. Detailed balance at the micro level yields equilibrium at the macro level, and mild violations of detailed balance describe steady-state non-equilibria where entropy production remains positive. Attempts to reverse macroscopic flows must therefore either reduce the number of accessible microtrajectories, for example by confining the system and lowering its temperature, or supply information that selects the exceptional trajectories that go against the drift. There is also the matter of the initial condition of the observable universe. The large-scale arrow we observe seems intimately related to the fact that the early universe was in a state of extraordinarily low gravitational entropy. Uniform matter distributions in an expanding universe have lower gravitational entropy than clumped distributions because gravity wants to form structure, and structure formation releases energy that can heat surrounding degrees of freedom. As the universe expanded and cooled, free energy became available to drive local decreases in entropy. Stars formed, planets cooled, life arose, while the total entropy increased because the radiation fields and diffuse matter carried away the disorder. Reversing the arrow on cosmological scales would require returning the large-scale degrees of freedom to something like that early smoothness. But the dynamics of general relativity and the second law disallow any practical path to that outcome without extraordinary conditions that we have no evidence exist. One might wonder whether the small violations of T-symmetry in weak interactions could serve as a fundamental seed for macroscopic irreversibility. The answer appears to be no. The thermodynamic arrow is robust in classical and quantum systems that do not involve weak processes in any significant way, and its emergence is already fully accounted for by typicality and coarse graining given a special low entropy beginning. The weak force violations are fascinating and important for understanding matter-antimatter asymmetry in cosmology, but they are not the engine that cools your tea or keeps broken glass from reassembling itself. Another scientific thread concerns the cost of measuring and controlling systems at the precision required for reversal. Measurement in quantum mechanics is not just passive observation, it is an interaction that entangles the system with the apparatus, and, through the apparatus, with the environment. To reverse a quantum evolution, you must reverse not only the unitary part of the system's dynamics, but also the entanglement with everything that has learned about the system's state. If the environment has many degrees of freedom, and if they are not under your control, the cost of reversing that entanglement rises beyond feasibility. Decoherence theory quantifies how quickly quantum superpositions become effectively classical mixtures when coupled to an environment. The same mechanisms seal off macroscopic reversal by distributing phase information into places you cannot reach. With these pillars in place, it becomes easier to answer the question with precision that still permits wonder. If by reversing the flow of time we mean making an entire macroscopic scene unhappen, the scientific obstacles are not merely practical, but structural. You would need to isolate the scene to a degree that forbids information leakage, measure or compute a description of its microstate with fantastic resolution, and apply a sequence of operations that implement the exact time-reverse dynamics faster than perturbations ruin the plan. Each requirement scales poorly with system size. The environment, air, walls, the Earth itself, acts as a vast reservoir that records tiny pieces of the story and refuses to give them back without a price. If instead we are content with local reversals of specific processes, the scientific answer is steadier. Yes, waves can be refocused. Yes, spin ensembles can be rephased. Yes, quantum evolutions can be unwound with carefully engineered negative Hamiltonians. The limits are clear and quantifiable. Bandwidth and aperture in acoustics and optics. Coherence times and control errors in magnetic resonance and quantum devices. Thermal noise and coupling strengths in all cases. These limits do not challenge the second law. They illustrate how the macroscopic arrow emerges from microscopic symmetry once you account for information, control, and coupling. There are a few additional notions that round out the scientific picture. The fluctuation dissipation theorem ties the response of a system to small perturbations to the spectrum of its spontaneous fluctuations at equilibrium. Dissipation is a kind of forgetting. It is the way a system pays for being driven. Fluctuations are the reminders that microscopic motion never ceases. If you want to reverse a dissipative process, you must either undo the forgetting, which means reacquiring the lost information, or supply external work in a way that reconstructs the correlations without creating more disorder elsewhere than you remove locally. The accounting is unforgiving, but transparent. Wherever you move the disorder, the books, must balance. There is also the quiet fact that some processes look irreversible only because we describe them with effective equations that throw away details. The Navier-Stokes equations for fluids include viscosity terms that break time reversal symmetry. Those terms arise by coarse-graining molecular dynamics. If you zoom in and treat the molecules with time reversal invariant equations, the apparent asymmetry disappears at that level, only to reappear when you average over many interactions. Reversal, then, is as much about the level of description as it is about the system itself. The more coarsely you describe the world, the sharper the arrow becomes. Finally, there is a scientific humility that is not a retreat, but an organizing principle. The macroscopic arrow is a statistical emergent contingent on initial conditions and the limits of control. Within those limits, the scientific program of reversal is not to conquer the arrow, but to map where it bends. Build systems small enough that you can specify their states, isolate them so that leaks are slow, design controls that implement negative evolutions with minimal error. Quantify how fidelity decays as size grows and as the environment whispers into your apparatus. In doing so, you do not reverse the universe. You learn how the universe shares and hides information, and you sometimes persuade a small part of it to walk a few steps back with you. In classical mechanics, time reversal begins as a simple map on trajectories. If you write a particle state as a point in phase space with coordinates for position and momentum, reversing time corresponds to taking the same path with momenta negated. The Hamiltonian equations preserve phase space volume, so running the movie backward traces a lawful solution provided you change the sign of all velocities. This rule extends to fields. For a classical electromagnetic field, the time-reversed configuration keeps the electric field and flips the magnetic field because magnetic fields are tied to motion of charges. The operation is precise. It is not a vague idea of going backward, but a transformation that takes a valid history into another valid history under the same equations. Quantum theory asks for more care. Time reversal is not represented by an ordinary unitary operator, but by an anti-unitary operator, which means it involves complex conjugation in addition to a rotation in Hilbert space. Under this operation, momenta change sign, spin angular momenta flip, and phase relations are conjugated. The Schrödinger equation is symmetric under this transformation if you also transform the Hamiltonian appropriately. For most interactions, this symmetry holds. There are measured exceptions in weak interactions where certain decays prefer one temporal orientation ever so slightly. The CPT theorem assures that if you invert charge, parity, and time together, the full theory is invariant, but individual factors can be violated. These microscopic T violations are small and specific. They do not power the thermodynamic arrow that governs a cooling cup or a diffusing perfume. The difference between microscopic reversibility and macroscopic irreversibility becomes easier to see when you formalize the way information is discarded. Begin with a distribution of microstates evolving under Hamiltonian flow. Liouville's theorem keeps the fine-grained Gibbs entropy constant because the flow stretches and folds the distribution without changing its volume. Now, admit that no macroscopic observer tracks the fine filaments that develop under this flow. Coarse-grain phase space into cells larger than the filaments. As the distribution is stirred, it spreads across more cells, and the coarse-grained entropy rises. That rise is the second law in practical form. It is not that the world has created disorder in the fine dynamics. It is that your description has lost the precise correlations needed to tell one filament from another. This way of speaking resolves two classic objections at once. Loschmidt's paradox notes that for any entropy increasing trajectory, there is a corresponding entropy decreasing a time reverse trajectory. The paradox dissolves when you acknowledge that the entropy decrease requires the initial microstate to be an exquisitely contrived arrangement, one that ordinary preparation procedures do not generate. Zermelo's recurrence paradox points out that, in a bounded phase space, trajectories return arbitrarily close to their starting points after astronomical times. Recurrence is true at the fine-grained level. The coarse-grained perspective shows why you almost never witness it. The recurrences are so remote and delicate that any coupling to an environment destroys them long before they matter. Statistical mechanics adds sharper statements. Near equilibrium, microscopic transition rates satisfy detailed balance, a relation that eliminates net flows and makes time reversal indistinguishable at the level of macroscopic currents. When you drive a system out of equilibrium, you can still write exact relations that tie the statistics of forward and backward fluctuations together. The Jarzynski equality says that the exponential average of the negative work done during a non-equilibrium transformation equals the exponential of the negative free energy difference between the endpoints. The Crookes relation compares the probability of observing a given amount of work in the forward protocol to observing the negative of that work in the reverse protocol executed on the time-reversed system. These theorems do not license macroscopic reversal. They quantify how rare entropy-decreasing events are and show that the second law emerges as a statement about averages over distributions with long but exponentially suppressed tails. Information theory renders the same terrain in a different language. The second law can be read as a statement about the impossibility of compressing away ignorance without cost. Landauer's principle ties the erasure of one classical bit to a minimum heat dissipation proportional to the ambient temperature. Bennett showed that computation without erasure, logically reversible computation, avoids this cost at the step of logical mapping, but cannot avoid physical costs associated with initialization, error correction, and coupling to a finite temperature environment. Can we compute without leaving crumbs of heat behind? In any physical implementation, controlling and measuring at the precision required for reversal forces you to pay in energy and entropy elsewhere. The daemon that sorts molecules across a door reduces entropy locally, but only by creating and then erasing records. When those records are cleared, the environment heats, and the global accounting remains intact. When you move from generalities to concrete systems, the lessons sharpen again. In acoustics, time reversal mirrors capture a complicated sound field with an array of microphones, reverse the recorded signals in time, and play them back from co-located speakers. The re-emitted field refocuses to its source despite multiple scattering and reflections because wave equations are linear and time-symmetric under the appropriate transformations. The fidelity of refocusing depends on aperture, bandwidth, and loss. Portions of the field that you fail to capture play the role of an effective environment, carrying away correlations that you cannot reconstruct. In optics, phase conjugation uses a nonlinear medium to generate a wave whose complex amplitude is the conjugate of the incoming one. That conjugated wave retraces its path through a distorting medium, undoing aberrations. Losses and inhomogeneities limit performance by attenuating and when information dissolves into the crowd, where would you start to call it back? Magnetic resonance provides a particularly clear window on engineered unwinding. Suppose an ensemble of spins processes in a magnetic field with slight inhomogeneities. Initially aligned, the spins dephase as they accumulate different phases, and the macroscopic signal decays. A well-timed radio frequency pulse flips the spins, causing phase errors to rewind, and the signal reappears as an echo at twice the initial evolution time. introduce controlled interactions or gradients, and apply sequences that approximate the negative of the effective Hamiltonian, and you can produce Loschmidt echoes that probe how quickly perturbations degrade reversibility. The decay of echo fidelity aligns with measures of chaos in the corresponding classical dynamics and with spectral statistics in the quantum regime, linking the abstract language of sensitivity to concrete loss of refocusing. Diffusion offers another perspective. The diffusion equation is first order in time with a Laplacian that smooths gradients. Change the sign of time in the equation, and you obtain anti-diffusion, which takes smooth profiles and inflates tiny fluctuations into singularities. Mathematically, solving the backward heat equation is ill-posed. Arbitrarily small noise in the data produces arbitrarily large errors in the solution. Physically, anti-diffusion is the precise reversal of uncountably many microscopic motions that were ignored when the diffusion equation was derived. To implement it, you must reconstruct those motions or specify boundary conditions with unachievable precision. Regularizations can produce partial reconstructions over limited times by suppressing high-frequency components, but the general message stands. Reversing a coarse-grained, irreversible process requires information that the coarse graining discarded. Quantum mechanics adds the central complication of entanglement. When a system becomes entangled with its environment, phases that were well defined in the isolated system are transferred to correlations with external degrees of freedom. Decoherence theory expresses this transfer in master equations that, under broad conditions, take Lindblad form. The system's density matrix evolves with a unitary part and dissipative terms that represent coupling to the environment. Reversing the system alone cannot recover phases that have migrated into environmental correlations. You would have to reverse the dynamics of the combined system and environment, which for macroscopic apparatus means controlling an astronomical number of variables. Decoherence times in warm, wet environments are often extremely short, which is why macroscopic objects behave classically and why macroscopic reversal is such a remote dream. There are, however, regimes where the drift toward equilibrium is unusually slow and memory persists. In integrable systems with many conserved quantities, relaxation does not reach an ordinary thermal state, but a generalized equilibrium that retains information about the conserved charges. Small perturbations break integrability and eventually allow thermalization, yet pre-thermal plateaus can last for long times. Many body localization provides another route to persistent memory, where disorder and interactions conspire to prevent energy and information from spreading. In these cases, you can, for longer than usual, design operations that nudge the system toward a previous configuration because competing processes that would ordinarily scramble information are suppressed. Even here, the path to full reversal is blocked by residual couplings and rare processes that ultimately restore typical behavior. The difference between integrable and chaotic systems plays a role in reversibility. Classical chaos, characterized by positive Lyapunov exponents, means that tiny perturbations grow exponentially in time, making reversal exquisitely sensitive to error. Quantum systems do not exhibit chaos in trajectories, but they do show signatures in spectral statistics and in the behavior of out-of-time ordered correlators, which measure how quickly operators fail to commute when evolved in time. These correlators grow in systems that scramble information rapidly, signaling that any attempt to reverse a specific evolution must contend with an explosion of operator complexity. In practical terms, the control sequences you need to implement the negative of a complex many-body Hamiltonian become deep and delicate, and small calibration errors destroy fidelity. Resource theories of thermodynamics formalize these intuitions into theorems. They define a set of allowed operations, thermal operations, that couple a system to a heat bath at fixed temperature while conserving energy, and ask what state transformations are possible under those constraints. The answers are expressed in terms of monotones, generalized free energies that cannot increase under the allowed operations. These monotones form a family rather than a single number when coherence is present, reflecting the richer structure of quantum resources. Such frameworks prove that even with catalysts that are returned to their initial states and with access to baths, you cannot transform arbitrary states at will. The ordering is partial, and most transitions that would amount to large-scale reversal are forbidden unless you supply additional resources quantified by these monotones. Feedback control tightens the link between information and thermodynamics. In feedback experiments, a controller measures a system and then applies a protocol conditioned on the outcome using information to extract work. Generalized fluctuation relations incorporate the mutual information gained in the measurement and show how it shifts the work bounds. Colloidal particle experiments and single-molecule pulling have demonstrated these effects quantitatively. These demonstrations are as close as physics comes to a daemon that works. They also make explicit that the daemon's memory and erasure cost complete the global entropy budget. Reversal-like behavior, concentrating energy, sharpening distributions, appears, but always within the constraints of measurement costs and environmental coupling. Cosmology sets the stage for all of these discussions by fixing boundary conditions. The observed universe began in a state of remarkable smoothness, as seen in the near uniformity of the cosmic microwave background, with tiny fluctuations imprinted by quantum processes during inflation. Smoothness in gravitational degrees of freedom corresponds to low gravitational entropy, because gravity's natural evolution is to clump, and clumping releases energy that increases entropy in radiation and matter. The low entropy beginning made an enormous reservoir of free energy available for structure formation and for the local decreases in entropy that life and technology achieve. Any program to reverse the macroscopic arrow would have to negate this large-scale gradient in some way, but general relativity and the second law together prevent such engineering except in speculative models with ingredients we do not observe. There is an alternative picture of time that tries to dissolve the very question by changing perspective. The arrows of time become features of the correlations and of the boundary conditions, not of a global river that could run one way or the other. From this vantage, reversing time would mean moving to a different path through a fixed structure, which is not something physical agents can accomplish. Whether you prefer this view or the more familiar one of evolving states, the operational conclusions are the same. Local, engineered unwinding is possible under strict conditions. Global reversal is out of reach. With these foundations, you can set criteria for what counts as a meaningful reversal in the laboratory. You must specify the subsystem of interest, the degree of isolation achieved, the accuracy with which you know and control the Hamiltonian, and the measures you will use to judge success. Fidelity is one measure, comparing the actual state after your unwinding protocol to the initial state. Echo amplitudes are another, integrating over certain observables that summarize coherence across many degrees of freedom. You must quantify decoherence rates, control errors, and leakage to unmonitored modes. If possible, you should estimate the entropy balance in the extended apparatus, including the work required to measure and drive, and the heat dumped into the surroundings. When these are in hand, you can speak precisely about how close to reversal you have come. A similar discipline clarifies discussion about reversing psychological time. Our sense of temporal flow is linked to memory formation, prediction, and control. Memories are material traces in neural tissue, maintained by metabolic work and protected by redundancy and error correction at the biochemical level. To reverse a memory is to reverse a cascade of molecular changes across networks of cells. The same thermodynamic accounting applies. The brain maintains low entropy locally by exporting entropy through metabolism. The asymmetry of experience, remembering the past, not the future, arises because traces accumulate in one temporal direction given the boundary conditions of our world. No known mechanism flips that asymmetry globally. You can manipulate perception to disturb the sense of order and duration, but you are not reversing the physical processes that underwrite the arrow. Even the examples that most resemble reversal in spirit are careful not to promise more than they can deliver. A time reversal mirror does not make broken object heal, it reconstructs a specific wavefront. A Hahn echo does not restore every microstate of a spin bath, it cancels the dominant dephasing pathway under precisely designed pulses. Quantum unwinding protocols do not roll back measurement-induced entanglement with a room, they reverse unitary parts of the dynamics on a small Hilbert space. Each success is a lesson about where the equation's time symmetry can be harnessed, and where the combinatorics of large systems and the ubiquity of environmental coupling make reversal fade. There remains the practical ambition of engineering systems where the arrow bends more easily. You choose architectures with long coherence times, high fidelity controls, and strong isolation. Trapped ions with clean motional modes, superconducting circuits with carefully filtered environments, neutral atoms and optical lattices with tunable interactions. You characterize noise sources and design dynamical decoupling sequences to average them away. You implement echo-like protocols at multiple scales, combining them with error correction that encodes information redundantly so that localized losses can be repaired without full reversal. In these efforts, you are not in conflict with the second law. You're using energy and information to hold order in place, buying time against the statistical tide. As you look back across this landscape, a consistent picture emerges. The laws at small scales are largely symmetric under time reversal, and that symmetry manifests as exact identities relating forward and backward fluctuations, and as formal transformations that map valid evolutions into each other. The arrows that dominate macroscopic life arise from boundary conditions, coarse greening, and the proliferation of degrees of freedom that expedite the loss of accessible information. Reversal at large scales would require undoing entanglement and restoring correlations across systems so extensive that the cost exceeds any plausible resource. Reversal at small scales is real and useful, provided you define the subsystem carefully and accept that the environment will write your work into its own degrees of freedom. If you continue this line of thought into technology, the program becomes constructive rather than quixotic. In communication, time reversal focuses energy through complex channels, improving delivery without increasing total power. In quantum information, echo protocols and error-correcting codes unwind specific error channels and preserve coherence long enough to perform useful computation. In non-equilibrium thermodynamics, feedback protocols use information to sharpen distributions and extract work from fluctuations in ways that respect generalized second laws. Each of these is a local victory over dispersal, achieved by paying the correct price and respecting the limits of control. The original question asked whether we can reverse the flow of time. The answer, seen through the clearest glass we can polish, is layered. For entire macroscopic scenes, no. For carefully defined processes and well-isolated systems, yes, to a degree quantified by fidelity and limited by noise and coupling. For the world as a whole, the arrow is a statistical emergence set by initial conditions and by the inescapable friction between what the equations allow and what finite observers can control. The science does not steal the wonder from the question, it gives the wonder a shape you can hold. In scattering theory and wave mechanics, there's a precise sense in which going backward is encoded as a symmetry of the equations. Reciprocity theorems state that under broad conditions, the response measured at point A due to a source at point B equals the response at B due to a source at A. This reciprocity is a kind of time reversal shadow. It does not literally run the world backward, but it reflects the invariance of the underlying Green's functions when dissipation and non-reciprocal media are absent. When you add ingredients that break time reversal symmetry, magneto-optic effects in photonics, for example, the reciprocity can fail. giving devices like optical isolators that allow light to pass one way but not the other. These components do not create a macroscopic arrow by themselves, but they show how even linear wave physics can acquire directionality when materials couple fields to a bias that flips sign under time reversal. The classical electromagnetic field makes the same point in a more fundamental way. Maxwell's equations admit retarded and advanced solutions, waves that propagate outward from a source after it acts, and waves that seem to converge on the source before it acts. The equations are impartial. Our boundary conditions choose the retarded solutions. The world is full of absorbers that accept radiation, and the pass boundary condition is one of low incoming radiation from infinity, so the physically realized fields are the ones that radiate outward. Wheeler and Feynman once explored a theory in which all radiation is the result of interaction with the entire absorber content of the universe, a kind of global constraint that singles out retarded behavior. Whether or not one adopts that framework, the lesson remains. The equations are time-symmetric, and irreversibility appears when you pin down the boundaries. In quantum mechanics, the time reversal operation reaches into the structure of microscopic states themselves. For a spin 1/2 particle, time reversal flips the spin direction and takes complex conjugation of amplitudes, which has the notable consequence of producing Cramer's degeneracy. In systems with half-integer spin and no time reversal breaking fields, energy levels come in degenerate pairs. This is not about glasses reassembling. It is a statement about how symmetry constrains spectra. When you break the symmetry by adding a magnetic field, the degeneracy lifts and new pathways open for dynamics. The macroscopic arrow still comes from statistics and boundary conditions, but microscopic symmetry leaves fingerprints that can be measured with exquisite precision. Once you move from symmetries to experiments that try to unravel dynamics, you discover that the operative quantity is control fidelity. A pair of unitary evolutions, U and U dagger, would perfectly unwind if you could implement them without error. In a real laboratory, you implement a sequence of gates or pulses that approximate U and its adjoint. Each element carries calibration error, and each interval allows coupling to degrees of freedom you are not tracking. The fidelity with which the combined sequence returns a state to its origin typically decays as a function of the number of operations and the strength of uncontrolled couplings. This decay rate becomes a practical measure of how strongly the environment enforces the arrow, even when every individual step obeys time-symmetric rules. Quantum information gives a concrete language for this. Any unitary computation can be exactly reversed by running the adjoint circuit in the opposite order. Indeed, a standard trick called uncomputation cleans up in qubits, computational workspaces, by applying the inverse of the subroutine that created them, erasing garbage without a thermodynamic cost at the level of logical operations. But the physical implementation does have a cost. Gates have error rates, controls drift, and qubits decohere. Error-correcting codes exist to repair small mistakes, yet they require redundancy and continual syndrome measurements that themselves consume energy and export entropy. The logic can be reversible, the physics never fully is. The gap between these layers is another way to see why macroscopic reversal is elusive. As you scale from logic to implementation, the costs grow faster than your capacity to cancel them. Fluctuation theorems connect all of these ideas to measurable numbers. In single-molecule pulling experiments, a tiny polymer is stretched and relaxed along a protocol that changes too quickly for the system to remain in equilibrium. The work done fluctuates from run to run. When you form the exponential average of the negative work scaled by thermal energy, you recover a number determined solely by the equilibrium free energy difference between the end states. Even though each realization is far from reversible, the ensemble obeys an identity that could only hold if the underlying dynamics respected micro-reversibility. The tails of the work distribution, rare events in which the system gives back more than it takes, are suppressed but not forbidden. They're the statistical whispers of reversible equations underneath a macroscopic drift. A complementary demonstration comes from feedback-controlled colloidal particles. A micron-sized bead sits in a harmonic trap created by light. By measuring its position and adjusting the trap in real time, an experimenter uses information to extract work from thermal fluctuations. The average work extracted can exceed the naive bound set by the second law if you ignore information, but when you add the mutual information gained by measurement to the entropy balance, a generalized law is restored. The bead's motion can be steered into narrower distributions than passive relaxation would allow, and for a moment, the evolution looks like a reversal of diffusion. The price is paid in the controller's memory and in the heat released when that memory is reset. The daemon works, but pays its bill. Diffusion itself illustrates the difficulty of reconstruction. The forward heat equation takes an initial temperature profile and spreads it. The backward equation tries to reconstruct a sharper profile from a blurred one. Mathematically, this inversion is ill-posed. Small errors in the input become large errors in the output because the high-frequency components that would restore edges are the first to be smothered by noise. Regularization methods, penalties on roughness, priors on plausible shapes, allow partial reconstructions over finite times. They do not reverse the process. They instead inject external information about what the original profile could have been. This, too, is a prototype for time's arrow. To go back, you must bring knowledge that the forward process discarded. Thermodynamics and information make the same point with accounting. Suppose you attempted a grander reversal, not of a tiny system, but of a room. The microscopic state of the air alone requires on the order of Avogadro's number of variables to describe, and even if you compress the description to coarse cells, the number of bits required to specify a reversal at useful precision is astronomical. Landauer's bound tells you that writing and erasing these bits costs energy proportional to their number and to the ambient temperature. Even if you had a device that could control all the modes, the heat released by the bookkeeping would swamp any local decrease in entropy you could engineer in the room. The project fails not because equations forbid it, but because the resources required scale in a way that makes success self-defeating. It is natural to ask whether gravity changes this calculus. Gravity couples to everything, and through curvature tells matter how to move. General relativity allows space-times with closed time-like curves, paths that loop into their own pasts under exotic conditions. The construction of such curves usually requires stress energy that violates classical energy conditions, or arrangements that are unstable when quantum fluctuations are included. There is a conjecture, more a discipline than a theorem, that the laws of physics protect chronology. Hawking's argument invokes the growth of vacuum fluctuations near the formation of a closed time-like curve that would destabilize the geometry before paradoxes could take root. The technical details are subtle, but the weight of evidence points the same way our laboratory experience does. The equations permit exotic possibilities. The full accounting of fields and fluctuations turns most of them away. If ticks change their spacing, does the arrow change, or only the pacing? In strong gravitational fields or at high velocities relative to an observer, time intervals stretch or compress compared to those measured elsewhere. These are measured effects, and they are essential to technologies that require precise timing. They do not reverse time, they change relative rates. A clock brought down from orbit and set beside a twin on Earth will have recorded a different elapsed time. No paradox arises. The arrow points the same way on both world lines. The tick marks are simply spaced differently. The distinction matters because it reminds us that many linguistic gestures toward reversing time are really about altering duration, not inverting causation. When a charge accelerates, it radiates energy away. You do not see radiation spontaneously converge to accelerate a charge in the absence of a source. This asymmetry is again about boundary conditions and typicality. Advanced solutions exist, but arranging the incoming fields so they focus at the appropriate place and time with the correct phase to accelerate a charge is a staggering coordination problem. The universe does not deliver such conspiracies unbidden. When you average over the plausible states of faraway fields, the retarded behavior dominates. The small domain in state space where advanced behavior would occur is not forbidden. It is statistically invisible. Many-body physics offers another window through the notion of scrambling. In systems that scramble quickly, local information disperses into non-local degrees of freedom, making it inaccessible to observers with limited control. Out-of-time ordered correlators quantify this spread. Their growth is a sign that a small perturbation at an early time affects many degrees of freedom at a later time. Reversal in such systems demands that you reverse not just a simple evolution, but a complex operator that has grown in support and complexity. The overhead and control scales badly with system size and with time. In contrast, in systems that scramble slowly, integrable or many-body localized systems, information remains in identifiable places longer, and limited reversal protocols work better. The physics does not bar return, it hides the map. If you step back to computation, there are architectures designed to minimize dissipation by avoiding erasure. Reversible logic gates, such as the Toffoli gate, can implement any computation without losing information at the logical level. Adiabatic or ballistic computing schemes attempt to move signals without friction and to compute without heat. But these ideals collide with noise, finite switching speeds, and the need to set initial conditions and read out final states. Error correction can make logical reversibility robust, but at the cost of redundancy and active intervention. The principle stands. Logical reversibility avoids a certain class of thermodynamic costs, but its translation into hardware is bounded by the same environment that writes the arrow in everything else. A related scientific theme clarifies the distinction between prediction and retrodiction. Predictive inference uses current data to estimate future states. Retrodiction uses current data to estimate past states. In many linear Gaussian systems, the mathematics is symmetric. The same common filter that predicts forward has a backward counterpart that reconstructs backward. But when you add measurement noise, model error, and nonlinearities, retrodiction becomes less stable. Errors that are tolerable in forward propagation blow up when run backward, an echo of the ill-posed nature of anti-diffusion. In meteorology, for example, the equations are deterministic and time-symmetric, yet weather is much easier to forecast forward over short horizons than to reconstruct backward beyond what observations allow. The physical world inherits these limitations from the interplay of dynamics and ignorance. There is a cosmological echo of this in the so-called past hypothesis, the assumption that the early universe occupied a very special, low-entropy macrostate. This hypothesis, in conjunction with time-symmetric laws, is enough to generate the observed arrow. Competing ideas, universes that bounce so that arrows point away from a central low-entropy surface, or scenarios where inflation selects special initial conditions, change the storytelling but leave the operational statements intact. The direction we experience is a global fact about the whole, not a local term in the equations we might toggle. A dream of reversal that ignores this scaffolding is like a dream of sailing uphill without wind. Even still, one learns to make headway by narrowing ambition. In optics, adaptive optics does not reverse atmospheric turbulence. It measures phase distortions and pre-distorts a wavefront so that it arrives planar at a telescope's pupil. In communication through complex media, one accepts that the channel scrambles signals and then designs pre-inverses that undo the scrambling at the receiver. In NMR and electron spin resonance, composite pulses cancel known imperfections in control fields, yielding better echoes and longer coherence times. Each of these is a form of engineered unwinding that works by anticipating dispersal and acting before it becomes irreversible. The logic is compatible with the arrow because it pays for local order with external work and information. You can make the cost of global unwinding more vivid with a back-of-the-envelope count. Consider a liter of air at room temperature. The number of relevant microscopic coordinates you would need to specify, positions and momenta for each molecule to modest precision. To reverse a half second of its evolution, you would need to measure, store, and then act upon a comparable amount of information faster than perturbations introduce new error. Writing and erasing huge bits at room temperature would, by Landauer's bound, release on the heat vastly larger than the thermal energy in the air you hoped to rewind. These are rough numbers, but they are directionally correct. They show that the second law is not just a slogan, it is a scaling argument hiding in plain sight. The cleanest piece with all of this is not resignation, but strategy. Define the subsystem, control the Hamiltonian, isolate the environment. Quantify the information you must preserve. Decide what fidelity counts as success. Then design an unwinding protocol that is honest about what it cannot repair. In this frame, time reversal is not a metaphysical ambition, but an engineering discipline. You do not make yesterday unhappen. You keep a fragile pattern from joining the sea of possibilities for a little longer than it otherwise would. Where the equations are kind and the noise is quiet, the discipline succeeds. Where the equations are neutral and the noise is loud, the discipline falters. There are still speculative corners worth visiting briefly, if only to set boundaries. Some models imagine closed, time-like curves that can be navigated self-consistently, where any attempt to alter the past merely selects a path that was always consistent. Others explore quantum versions of such curves that allow states to interact with their own histories, with predictions that break linearity and in some renditions allow impossible operations like perfect cloning. These constructions are mathematically intriguing, but they sit far from regimes tested by experiment and often collide with the structure that makes quantum theory predictive. They do not offer a road to reversal in the operational sense developed here. A more grounded frontier looks for media that emulate time reversal effectively by modulating properties in time. Time-varying metamaterials can mix frequencies and wave vectors in ways that mimic the action of phase conjugation without a traditional non-linear crystal. In acoustics and elasticity, spatiotemporal modulation can produce non-reciprocal transport that directs energy flow. These do not reverse the global arrow, they provide additional levers with which to steer waves locally against the default drift of dispersion and loss. In every case, the price appears on another ledger: the energy to modulate, the noise introduced by switching, and the complexity of control. As the terrain expands, the central shape remains. Microscopic laws are mostly time-symmetric. The arrows we experience arise from special boundary conditions and the combinatorics of large systems. Reversal, in the strong sense, is blocked by the need to gather and act upon information that disperses faster than any controller can keep up with, and by the necessity of paying thermodynamic costs that scale unfavorably. Reversal in the modest sense is common and useful. Waves can be refocused, coherence can be restored, specific evolutions can be unwound with designed adjoints. Between these poles lies a spectrum of techniques whose limits can be calculated and whose payoffs can be measured. If the question still glows after all this detail, it may be because it is actually two questions braided together. One is physical: can the dynamics be made to run backward? The other is human: can loss be undone? Physics answers the first with a layered yes and no, carefully qualified. The second is a matter for craft and patience. Local repair happens everywhere in nature and technology. It is not time reversal, but it is how pockets of order persist in a universe that drifts. If we keep learning how to hold those pockets gently, by knowing more, by isolating better, by designing evolutions that have clean inverses, we inch closer to the edge where the law's symmetry becomes visible again. There is more to put on firm ground: a closer look at how fluctuation theorems are proved and tested, an exact account of decoherence rates in representative environments, detailed examples of echo protocols in different physical platforms, and the cosmological arguments that turn low early entropy into an arrow that runs through every laboratory. Each edition will not change the answer, it will make the map sharper, the costs clearer, and the line between what can be unwound and what must be let go more honest. In particle physics, there are clean quantitative tests of microscopic time reversal symmetry that do not rely on thermodynamics at all. Neutral kaons provide one route. If you prepare beams that evolve between particle and antiparticle states, you can compare transition probabilities under conditions that isolate T-odd effects. A measurable asymmetry, historically known as the Kabir asymmetry, signals genuine violation of time reversal invariance at the level of weak interactions. In the B-meson system, entangled pairs produced in electron-positron collisions allow a direct comparison of transitions that are each other's time reverse. By tagging initial and final flavor or CP eigenstates and exchanging what you call initial and final, one can measure a difference that cannot be blamed for CP alone. The observed T violation is small and exquisitely specific. It confirms that time reversal has a precise meaning in the fundamental theory, and that for certain processes, nature slightly favors one temporal orientation. These effects, however, are far too tiny and too restricted to account for the thermodynamic arrow governing macroscopic phenomena. The kinetic theory of gases gives a different lens on irreversibility through Boltzmann's H theorem. The H functional, an integral over the single particle distribution weighted by its logarithm, declines monotonically along solutions of the Boltzmann equation toward its minimum at the Maxwell-Boltzmann distribution. The theorem's proof rests on the Stoß-Saul-Ansatz, or molecular chaos assumption. Pre-collision velocities of particle pairs are statistically uncorrelated. This is not a statement about microscopic dynamics. It is a statistical property of typical dilute gases that do not harbor fine-tuned correlations. The theorem, then, is conditional. If the two-particle distribution factorizes in the manner assumed, the coarse-grained entropy rises. The modern perspective behind propagation of chaos shows how, in the low-density limit with short-range interactions, such factorization emerges from many body dynamics for large classes of initial data. In this way, the H theorem becomes a rigorous bridge from reversible microdynamics to emergent irreversibility without invoking anything mystical, only the statistics of large systems and the practical absence of conspiratorial initial correlations. At the level of fluids, irreversibility shows up in turbulence, even though the Euler equations for an ideal fluid are themselves time reversal symmetric. The Navier-Stokes equations add viscosity, which breaks time reversal invariance and brings dissipation explicitly into the model. Yet, an intriguing feature remains in the inviscid limit. Experiments and simulations display a persistent forward energy cascade in three-dimensional turbulence, where energy injected at large scales flows to smaller scales and is dissipated as heat at the smallest. Onsager conjectured that sufficiently rough, weak solutions of the Euler equations can dissipate energy anomalously, without explicit viscosity, so that the limit of vanishing viscosity retains a finite dissipation rate. This shocking outcome turns irreversibility into a property of the solution class rather than the equation's coefficients. Time asymmetry is visible in statistics such as the skewness of Lagrangian acceleration or the unequal probabilities of forward and backward pair dispersion, highlighting that turbulence writes an arrow into the data through cascade structure and intermittency even when formal symmetries of the ideal equation survive. There is a practical corollary in numerical dynamics. Reversibility on paper does not guarantee reversibility in computation. Symplectic integrators for Hamiltonian systems preserve phase space volume and exhibit shadow Hamiltonians that keep long-time behavior faithful in aggregate. Still, in chaotic regimes, round-off and discretization errors grow exponentially with time. Exact bit-level reversibility is quickly lost unless the scheme is explicitly designed to be bit reversible. Special integrators that store and reuse least significant bits can run trajectories backward exactly on a computer, but only by turning the computer into part of the physical model. You are then reversing the arithmetic as well as the motion. The lesson generalizes. In any attempt to unwind a many-body evolution, errors act like an environment. They scramble phase relations and amplify forward, and reversing them requires knowledge of and control over the bookkeeping layer as well as the physics you thought you were simulating. Black hole thermodynamics adds an extreme case where time's arrow is stitched into geometry. A stationary black hole is assigned an entropy proportional to its horizon area and a temperature related to its surface gravity. In a semi-classical calculation, black holes radiate thermally and eventually evaporate, apparently turning pure states into mixed radiation and creating a one-way arrow. Information falls in, featureless heat flows out. If taken literally, that would violate unitarity and make time asymmetry fundamental. The modern consensus, informed by dualities in quantum gravity and by calculations of entanglement entropy in evaporating spacetimes, suggests that the full evolution is unitary. The entropy of the radiation follows a page curve, rising and then falling as correlations leak out. Island formulas in semi-classical gravity compute this behavior by including regions inside the horizon in the entanglement wedge of the radiation. None of this makes evaporation reversible operationally. It shows instead that the appearance of irretrievable loss came from discarding global correlations. The arrow you see near the horizon arises once again from coarse graining and limited access, even in the most extreme thermodynamic system we know. Stochastic thermodynamics extends fluctuation theorems to single, noisy trajectories and provides a calculus for entropy production in small systems. A biomolecule forced by an optical trap executes a Lagrange dance, and along each sample path, you can define heat, work, and entropy production consistent with the first and second laws. Integral fluctuation theorems guarantee that the exponential of minus the total entropy production averages to 1, while detailed versions relate the probability of a forward trajectory to that of its time-reverse counterpart under the reverse protocol. In quantum versions, you must account for measurement back action and define work through two projective measurement schemes, or via interferometric protocols that reconstruct characteristic functions. Experiments with superconducting qubits and trapped ions have verified these identities, reinforcing the message: micro-reversibility remains true, while entropy production measures how much the statistics tilt toward histories that align with the macroscopic arrow. Biology supplies systems where local reversals are not metaphors, but operational modes. The ATP synthase is a rotary machine. Under physiological conditions, a proton gradient drives rotation that catalyzes ATP formation from ADP and phosphate. In vitro, Applying torque with a magnetic bead can spin the F1 motor backward, forcing ATP hydrolysis to run in reverse and synthesize ATP, or vice versa. The enzyme is a molecular device that can operate in both directions depending on boundary conditions. This is not a violation of the second law. It is a demonstration that small systems can swap the roles of engine and refrigerator when the sign of affinities changes. Kinetic proofreading in DNA replication is another instructive case. Improved accuracy is purchased by consuming extra chemical-free energy and thus producing more entropy, making the time asymmetric selection of correct nucleotides more reliable. The arrow is not broken. It is harnessed with costs that can be measured in ATP molecules per bit of reduced error. Chemical reaction networks formalize this trade-off at the level of reaction graphs. When detailed balance holds, all cycles in the network have zero affinity, and there are no sustained currents. The stationary distribution is in equilibrium. Break detailed balance by chemostating certain species or by periodically driving reaction rates, and cycles acquire non-zero affinities that power persistent fluxes and dissipation. Schnackenberg's network theory expresses entropy production as a sum of cycle currents times their affinities, clarifying how housekeeping dissipation maintains non-equilibrium steady states, while excess dissipation accompanies transitions between them. In enzymatic turnovers observed at the single molecule level, fluctuations and cycle completions obey fluctuation relations and thermodynamic uncertainty relations, or TURs, bind the relative precision of currents by the entropy dissipated. The TURs make precise a speed-precision-dissipation trade-off. To make a biochemical clock more regular without slowing it down, you must spend more free energy. A separate, complementary set of limits comes from finite time thermodynamics. Reversible quasi-static processes set ideal bounds, Carnot efficiency, minimal work theorems, but require infinite time. When you insist on finite durations, there is an extra dissipation that depends on the speed and the pathway through control space. Thermodynamic length quantifies the minimal dissipation along a protocol through a Riemannian metric built from equilibrium fluctuations. The result is geometric. The least dissipative path between two macrostates in finite time is a geodesic in this metric, and the excess work scales with the square of the protocol speed. Counter-diabatic and shortcut to adiabacity techniques translate this geometry into control fields that suppress excitations in driven quantum systems, reducing dissipation at the expense of implementing additional Hamiltonian terms. The arrow does not vanish, it is negotiated with explicit costs for speed. A related frontier, quantum control with measurement, highlights the thermodynamic price of learning. Continuous weak measurement turns a quantum evolution into a stochastic trajectory conditioned on detector records. Bayesian filters estimate the state in real time, and feedback policies steer it. Each bit gleaned from the measurement apparatus is physically embodied, amplifiers add noise, records must be written, and sometimes erased. Generalized second-law inequalities incorporate mutual information terms and reveal when feedback can extract work from measurement-conditioned fluctuations. In circuit quantum electrodynamics and optomechanics, experiments now implement Maxwell-Demon-like protocols that stabilize otherwise fragile states. Reversal here means erasing specific error channels faster than they appear, and the price is paid in measurement back action and in the entropy exported by the classical controller. Beyond laboratory systems, there is an empirical way to infer errors from data when dynamics are not fully known. The idea of algorithmic independence of cause and mechanism proposes that, generically, the distribution of a cause and the conditional distribution of effect given cause are simpler, in an algorithmic sense, than the reverse pairing. In time series, this asymmetry can be exploited to infer temporal direction by comparing how compressible the forward model is versus the backward model. Physical processes that mix and disperse tend to be described by mechanisms that are simpler in the forward direction. The backward description needs finely tuned conditionals that reassemble correlations. While this approach does not replace dynamical laws, it supplies a statistical diagnostic consistent with the deeper picture. Reversal requires contrived structure that real data rarely support. There's also a corner where information theory and mechanics meet, through reversible computing at the hardware level. Logic gates like Fredkin and Toffoli are logically reversible. Compositions of them can implement any computation without the logical erasure that Landauer identified as dissipative. Adiabatic switching schemes move signals through energy landscapes slowly so that little heat is generated. Ballistic architectures aim to propagate information with almost no scattering. In practice, noise, leakage, and finite time operation introduce losses that must be corrected. Error-correcting codes and fault-tolerant constructions restore logical reversibility, but with overheads that translate to real power. These platforms do not turn time around. They minimize the entropy production per logical step. As devices shrink and clock rates rise, such considerations will set limits on how close to reversible computation our hardware can practically operate. Finally, there is a body of results on irreversibility in active and driven matter. Systems of self-propelled particles, cytoskeletal extracts, or colloids shaken by external fields, where microscopic time reversal symmetry is explicitly broken at the level of single constituents. The entropy production can be inferred from violations of fluctuation-dissipation relations or from probability currents in configuration space. Harada-Sasa relations tie measurable response correlation mismatches to energy dissipation. In these systems, arrows are not only emergent, but built in. Each self-propelled unit consumes fuel to sustain motion, and sustained motion generates circulating currents that have no equilibrium analogs. Reversal is not defined by unwinding to rest. It would require negating the drives or inverting them, which brings you back to the same accounting. Currents flip only when affinities do. If you collect these threads, the exact tests of T violation in weak processes, the conditional rise of Boltzmann's H under molecular chaos, the turbulent cascade statistical time asymmetry, the fragility of numerical reversal in chaotic systems, the unitary but operationally irreversible accounting in black hole evaporation, the trajectory level laws of stochastic thermodynamics, the bidirectionality of molecular machines with costs set by affinities, the cycle-based bookkeeping in reaction networks, the geometric cost of finite time protocols, the thermodynamics of measurement-based control, the asymmetries used to infer temporal direction, the engineering of logically reversible computation, and the explicit non-reciprocity in active matter, you arrive at a consistent scientific map. Nowhere does the core structure of physics forbid carefully engineered unwinding on small, well-isolated stages. Everywhere, the costs of scaling those stages up accumulate faster than control. The question, can we reverse the flow of time, resolves into a family of operational statements. For particular processes, under specified boundary conditions, with quantified resources and tolerances, one can make dynamics retrace themselves to within a fidelity that can be measured. For worlds larger than our instruments, the arrow is a robust consequence of statistics, geometry, and limited knowledge. There remain further domains we have not touched that deepen the same answer without circling back. The thermodynamics of learning in adaptive agents, speed limits in quantum metrology that relate precision to dissipation, irreversibility in glassy relaxation with its hierarchies of timescales, and gravitational wave back reaction as a radiative arrow in strong field dynamics. Each offers another carefully delimited setting where reverse can be asked with equations and answered with numbers. If you wish, we can walk into any one of them next, keeping the tone precise and the path new. In quantum foundations, there is a family of ideas that treats past and future on a more equal footing without inviting contradictions. One version is the two-state vector framework, where a quantum system is described not only by a state evolving forward from preparation, but also by a state evolving backward from a later post-selection. Between those boundary conditions, weak measurements probe observables with minimal disturbance and yield averages that reflect both forward and backward influences in the mathematics. This does not enable messages to the past. Signal locality is preserved because the correlations that look retrocausal average out when you don't condition on future outcomes. The point, rather, is that the formalism allows histories to be constrained at two ends at once. In such pictures, reversing time becomes a question about boundary data. If you could fix end conditions as well as beginnings, certain intermediate evolutions would be tightly guided. In practice, control over post-selection on macroscopic scales is as formidable as controlling every microscopic degree of freedom. The idea clarifies structure more than it changes engineering. A closely related mathematical idea appears in consistent histories. Instead of focusing on measurements, you consider sequences of coarse-grained projectors, yes-no questions about what happened when, and compute decoherence functionals that tell you which sets of histories can be assigned probabilities without contradiction. When histories decohere because interference has been washed out by environmental entanglement, you can speak about quasi-classical, time-ordered narratives. The arrow of time emerges through the choice of coarse graining and the low entropy boundary condition at one end of the history. Try to impose finely tuned reverse time narratives, and the decoherence functional generally refuses because the correlations they require are erased by ordinary coupling to the environment. The mathematics makes precise why narratives that look like reversal demand conspiracies the world does not supply. There are proposals in which time itself is not fundamental, but emergent from correlations. If you start from a global quantum state that satisfies a constraint like the Wheeler-DeWitt equation, no explicit time parameter, then relational time can be defined by using one subsystem as a clock and asking how the rest changes when the clock points to a particular value. In such constructions, dynamics arises from entanglement between clock and system. Probabilities are conditional. Another proposal, the thermal time hypothesis, says that given a state over observables, one can reconstruct a canonical flow, the modular flow, that acts like time evolution. Temperature and motion then affect perceived time because different states generate different flows. These frameworks do not hand you a lever to run the universe backward, they change the question. If time is a parameterization of change rooted in correlation structure, then reversal would mean inverting the correlations that give rise to the flow you perceive. The same obstacles, decoherence, dispersion of information, reappear in this language with new clarity. Cosmology adds further possibilities that are scientific enough to discuss and philosophical enough to invite reflection. One proposal, Penrose's whale curvature hypothesis, singles out the early universe as special because the gravitational degrees of freedom were in a low entropy configuration. The whale tensor, which encodes tidal distortions and gravitational radiation, was near zero at the Big Bang. As the universe evolved, gravitational entropy grew as structure formed and curvature became more complicated. In this reading, the arrow of time is the gradual activation of gravitational degrees of freedom. Reversal on cosmic scales would then require returning geometry to an exceptionally smooth state. Another idea from the same source, conformal cyclic cosmology, pictures the universe as an endless sequence of eons. Each eon ends in a state where massive particles have effectively disappeared, and the universe's geometry becomes conformally simple. That state can be mapped, after a conformal rescaling, to the Big Bang of the next eon. The arrow persists within each eon, but resets at the junction. If such a picture is correct, reversing time within an eon is not meaningful, but the universe as a whole contains a pattern that repeats in a generalized sense across boundaries. There is also a hypothesis that the universe is symmetric under a combined inversion of charge, parity, and time, not just in its laws, but in its global history. In one concrete model, a mirror anti-universe branches from the Big Bang in the time-opposite direction, realizing the CPT symmetry as a whole rather than merely locally in particle interactions. Observationally, such a model can have testable fingerprints in the neutrino sector and in the spectrum of primordial perturbations. Conceptually, it gives a clean answer to the question of initial conditions. There are none in the usual sense, only a symmetric whole in which each side perceives itself as moving forward. The idea does not make reversal available to agents within either branch. It reframes the arrow as a global feature of a larger symmetry. Philosophy has long asked whether time is something that passes or simply a dimension of a larger structure. Without repeating earlier viewpoints, it is useful to note the middle ground where physics meets metaphysics. If the correlations that define records and memories accumulate toward what we call the future, then for creatures embedded in such correlations, it is natural to experience becoming. New records appear, predictions become records, and the asymmetry is felt. A world in which correlations were symmetric in both temporal directions would feel alien because every attempt to form a stable memory would be countered by processes that erase it with equal ease. The fact that our world reliably keeps records is the practical signature of the arrow. A desire to reverse time is therefore partly a desire to unwrite records. In a universe that expends free energy to write them, unwriting is possible only locally and at cost. There is a neighboring question from the philosophy of causation, whether cause must always precede effect. Ordinary relativistic quantum field theory respects microcausality. Operators at space-like separations commute, forbidding faster-than-light signaling, and it enforces a causal order consistent with the light cone. Interpretations that use both advanced and retarded influences, such as the transactional picture where emitters and absorbers exchange offer and confirmation waves, are careful to reproduce these causal constraints. They allow you to imagine reconciliations in which the full story includes influences that run both ways in time, while agents remain unable to exploit them for paradox. Whether you adopt such an interpretation or not, the operational content remains. The set of signals that agents can send respects the same arrow everyone measures. On the side of complexity science, time's irreversibility shows up in the structure of models that compress the past to predict the future. Computational mechanics builds minimal predictive representations, epsilon machines, that capture all information from the past that is relevant for forecasting. The statistical complexity of such a model is the memory it needs to retrodict the past from the future is larger than the memory required to predict the future from the past. This directional asymmetry is measurable in data streams. Reversal demands more structure in the model because the forward dynamics throw away correlations that the backward model must supply. The difference does not replace thermodynamics, it complements it with an information-theoretic arrow that can be inferred without complete knowledge of underlying microdynamics. In glassy systems, irreversibility is written into a spectrum of relaxation times that stretches over many decades. When a supercooled liquid falls out of equilibrium, it explores a rugged energy landscape with barriers that grow at the size of cooperative rearrangements. Aging, a slow change of properties with waiting time, reveals that the system's effective clocks tick at rates set by history. Attempting reversal is not just a matter of inverting trajectories. It would require coordinating many collective rearrangements whose probabilities depend sensitively on how long the system has waited. The hierarchy of times replaces a single arrow with a choir of arrows that decohere from one another. The deeper the aging, the harder the choir is to tune back to a prior chord. In quantum metrology and control, speed limits quantify how fast states can evolve given bounded energy or control resources. Mandelstam-Tamm and Margulis-Levitin bounds set minimal times to traverse a given angle in Hilbert space. When you combine these with thermodynamic costs for measurement and control, you obtain trade-offs. how quickly you can steer a system back toward a target state, how precisely you can do it, and how much entropy you must produce in the process. These are not poetic gestures. They are inequalities that guide the design of feedback and error correction. The question of reversal becomes a design problem. Within these speed and cost limits, how closely can the adjoint of a noisy evolution be approximated before fresh noise undoes your work? There are also frameworks where the causal structure itself is treated as subject to quantum uncertainty. In process matrix formalisms and in experiments with indefinite causal order, operations can be arranged so that there is no fixed before and after between certain events. Yet the overall statistics remain consistent and acausal signaling is still forbidden. These scenarios do not reverse the flow of time. They broaden what counts as a legal wiring of operations. They remind us that our classical intuitions about order are emergent, and that at small scales, the skeleton of time can flex without breaking the rules that keep paradox at bay. Turning again to cosmology, without repeating earlier ground, there are ideas in which the arrow is tied to measures of algorithmic compressibility of the early state. If the initial conditions were simple in the sense of Kolmogorov complexity, short to describe, then typical evolutions would generate structures whose exact microstate descriptions become progressively longer. Logical depth, a measure of the computational effort needed to produce a given structure from a short program, grows as histories accumulate. Reversing a logically deep object is difficult because it requires not just undoing a configuration, but the computation that produced it. Stars, genomes, and cities are all logically deep in this sense. Their present forms encode long causal chains. The science here is not a theorem about entropy, it is a perspective that links the felt weight of history to measures of description and computation. Ethics and meaning enter as quiet companions to these scientific frames. If global reversal is out of reach, what remains is stewardship of local order. Repair, memory, and prediction are not lesser substitutes for reversing time. They are the operational ways finite agents resist dispersion. Error-correcting codes preserve messages under noise. Archives and fossils preserve knowledge under weathering. Ecosystems preserve structure under fluctuations by expending free energy. None of these actions violates the second law. They translate free energy into low entropy pockets that last longer than they otherwise would. The desire to reverse time becomes a commitment to build and maintain such pockets without pretending that the sea is not there. There is an attendant question about identity. If time could be reversed for a brain, would the experience of self unwind? From the scientific side, a brain is a dissipative structure maintained by metabolism and stabilized by redundancy. The patterns we call memories are distributed, noisy, and constantly rewritten. Unwinding them would require turning back biochemical cascades while preventing the rest of the organism and environment from reintroducing noise. Even if such unwinding could be implemented for a moment in a model system, the personal identity it would reconstruct would last only so long as isolation and control were perfect. The philosophical upshot is gentle. Persons are processes coupled to environments. Reversing the process is not a doorway to immortality, but a very delicate experiment in pattern restoration. When you knit them together, you arrive at a stance that is neither defeatist nor grandiose. The universe does not offer levers that make yesterday unhappen. It offers laws that let small patterns remember, return, and persist when they are tended with knowledge and care. There is an attendant question about identity. If time could be reversed for a brain, would the experience of self unwind? From the scientific side, a brain is a dissipative structure maintained by metabolism and stabilized by redundancy. The patterns we call memories are distributed, noisy, and constantly rewritten. Unwinding them would require turning back biochemical cascades while preventing the rest of the organism and environment from reintroducing noise. Even if such unwinding could be implemented for a moment in a model system, the personal identity it would reconstruct would last only so long as isolation and control were perfect. The philosophical upshot is gentle. Persons are processes coupled to environments. Reversing the process is not a doorway to immortality, but a very delicate experiment in pattern restoration. Finally, consider a picture in which the question, can we reverse the flow of time, resolves into a more constructive pair. Which flows can be locally unwound at what cost, and which records are worth protecting against the default drift. In this framing, physics remains precise. Fluctuation relations, control speed limits, decoherence rates, information theoretic costs. Philosophy remains a guide to meaning, what it is to keep a promise with the future, what it is to let some losses be final without making peace with neglect. When you knit them together, you arrive at a stance that is neither defeatist nor grandiose. The universe does not offer levers that make yesterday unhappen. It offers laws that let small patterns remember, return, and persist when they are tended with knowledge and care. There is a radiative imprint in gravity that behaves like a subtle signature of irreversibility. When a burst of gravitational waves passes through a region, freely falling test masses are left with a permanent displacement. After the wave train has gone, this gravitational wave memory is not a ringing that decays, it is a step in the metric that remains. In scattering language, energy and momentum are carried away to null infinity. Soft gravitron theorems and asymptotic symmetries relate this memory to conserved charges at the boundary. The classical equations admit time-reversed solutions in which finely tuned incoming radiation converges to cancel this displacement, but such initial conditions would require a conspiracy of phases across the sky. In ordinary astrophysical events, binary black hole mergers, neutron star collisions, the outgoing pattern is typical, not conspiratorial, and the memory records that typicality. As with electromagnetic radiation, the equations are symmetric. The realized boundary data are not. The permanent offset of mirrors in a laser interferometer would be a quiet, measurable arrow written into spacetime by a one-way flow of gravitational news. Another arrow orthogonal to time, yet deeply related to information, appears in the renormalization group. Coarse graining in space, Kadanoff blocking, Wilson shell integration, defines flows from microscopic descriptions toward effective theories at longer distances and lower energies. In two-dimensional quantum field theory, a theorem due to Zimolodchikov constructs a function c that decreases monotonically along these flows and equals the conformal anomaly at fixed points. In 4 dimensions, an analogous A function falls along the flow as shown by arguments that rely on positivity of certain correlators and on anomalies in curved backgrounds. These are not statements about clocks. They are measures of lost distinguishability when you ignore short-distance detail. Irreversibility in scale is captured by information theoretic monotones as well. Relative entropy between two states cannot increase under coarse graining maps, a quantum form of the data processing inequality. If you think of an RG step as discarding high-frequency information through a completely positive trace-preserving channel, then the impossibility of perfectly reconstructing the ultraviolet theory from the infrared one mirrors the impossibility of reconstructing a cooled cup's microstate from its macroscopic temperature and pressure. The flow here is in descriptive power. Models become simpler, and some distinctions become unreachable without putting the short scales back in. In practice, one can learn effective ultraviolet completions for specially structured systems, but the general inversion requires more than the infrared knows how to tell. Learning in physical agents and biochemical networks furnishes a third arena where arrows can be quantified. A receptor embedded in a cell membrane samples ligand molecules buffeted by thermal noise. There is a fundamental limit, known from Berg and Purcell's argument, on how precisely concentration can be estimated in a given time with a receptor of given size and binding kinetics. To approach that limit, the network downstream must process binding and unbinding events. storing information in chemical states that are themselves subject to noise. Stochastic thermodynamics relates the mutual information acquired per unit time to a minimum entropy production rate. Improved estimates require additional free energy consumption. Single-molecule experiments and theoretical bounds show that you can trade dissipation for precision or speed, but not abolish the trade-off. Reversal in this context would mean unlearning without cost, erasing stored correlations and recovering the energy spent to make them. At best, you can recycle a fraction by designing biochemical cycles that approach thermodynamic reversibility. The moment you insist on finite speed or finite error probability, dissipation returns. The same logic appears in engineered learners. A physical Bayes machine that updates parameters in real time must write bits to memory and perform comparisons. Landauer's cost attaches to any reset. Information geometry quantifies how much thermodynamic length a parameter update traverses. Fast jumps across a curved statistical manifold produce excess work, while geodesic moves minimize dissipation for a given speed. In adaptive control, there are learning rate heat inequalities that tie the rate at which a controller's internal model gains information about a process to the entropy it must export to the environment. These relations are not metaphors. They set floor costs in joules for a given improvement in predictive accuracy per second. If one asks for reversal after a learning episode, return the controller to its prior state without paying the bookkeeping, it is the same old impossibility in new clothes. There is a distinct kind of irreversibility in materials that remember their past. Hysteresis in magnets and shape memory alloys reflects a landscape of metastable states whose transitions depend on the path by which drives were applied. Even if the microscopic Hamiltonian respects time reversal, the macroscopic response features loops that do not retrace when the drive is cycled. Energy is dissipated on each loop. Heat flows into a bath. One can design quasi-reversible protocols that shrink the loop area by going slower and by avoiding avalanches. Yet the limiting ideal requires infinite time and perfect homogeneity. The arrow here is geometric in the space of control parameters. The loop orientation encodes direction. Undoing it in finite time would require canceling the dissipation by feeding back detailed microscopic information about which domains switched where. Again, a demand for knowledge that grows with system size. Strong field astrophysics adds a radiative arrow beyond gravitational memory. Compact binaries shed energy and angular momentum in gravitational waves described by multipole expansions, whose tail terms encode scattering off the curved background itself. Radiation reaction forces orbit inward. The in-spiral chirp's frequency sweep is an audible descent. A time reversed in spiral would require coherent incoming waves delivering energy to widen the orbit with the exact phase history that cancels all tails and nonlinear mixings. A construction allowed by the equations, but not by anything we observe in the sky. The system's coupling to unbounded radiation modes turns bound energy into far-field correlations you do not get back for free. That is the same radiative arrow we see in electromagnetism, translated to a regime where the bookkeeping is done by geometry. A different kind of direction arises in scale-free networks and critical phenomena. Near a continuous phase transition, the system is poised at a fixed point where correlation links diverge and dynamics slow down. Quenches that take a system across a critical point in finite time generate defects whose density scales with the quench rate by Kibble-Zurich arguments. The scaling laws are reversible in the equations, but asymmetric in practice. The route taken across the critical region matters because relaxation times blow up. Undoing a defect network by reversing the protocol would require holding near criticality long enough for annihilation to proceed, which in finite time leaves residues. The arrow is written by critical slowing down. The closer you steer to the fixed point, the longer the system remembers the path. Complex systems that adapt, ecosystems, markets, social groups, exhibit further asymmetries that can be framed without nostalgia or repetition. The macrostates that matter are defined by distributions over many interacting agents, with constraints and feedbacks that shift as the system learns or evolves. In evolutionary dynamics, selection accumulates information about the environment in the population's genotype distribution, a correspondence made quantitative by Fisher information and by links between fitness flux and entropy production. Mutational input and genetic drift act as noise. Adaptation pays an energetic cost in organisms, a resource cost in societies. Reversing an episode of adaptation would mean restoring the prior genotype or strategy distribution while extracting the costs that built it. A fantasy in general, a laboratory feat only for tiny synthetic populations under controlled chemostats. The arrow is the accumulation of adapted structure. The bound is the cost of writing it. There is also a scale-agnostic inequality that threads through all these cases, the data processing inequality. No local operation can increase the mutual information between two variables. No coarse graining can make two distributions easier to tell apart. In thermodynamic dress, this becomes the monotonicity of relative entropy under stochastic maps and quantum channels. It is the theorem behind practical statements like, a blurred photograph cannot be sharpened beyond what prior information supplies. A cooled gas cannot be unscrambled without bringing in knowledge and energy from outside. An effective field theory cannot be inverted without specifying ultraviolet detail that the infrared did not retain. If time reversal is make the world tell you exactly what it forgot, the data processing inequality says you must pay by supplying that information yourself. A final family of ideas treats the arrow as a byproduct of how we compress reality into models. When we build predictive representations, we choose summaries that are sufficient for forecasting forward. Retrodiction demands enough detail to distinguish among many pasts that all map to the same future statistics under the forward model. The mismatch, a model that is compact in one direction is bulky in the other, mirrors the thermodynamic story in an abstract register. Logical depth grows as histories lengthen. Minimal sufficient statistics for the forward task are often not sufficient for the backward task. This is not a law of nature, but a design constraint that intelligent agents rediscover. Store what the future asks for, let the rest go. All of these scientific threads bring us to a philosophical brink, where the question changes shape. If reversing time means recovering information that the forward flow disperses, then the central moral is not that reversal is forbidden, but that it is a resource-intensive transformation whose cost scales badly with size, speed, and coupling. The universe is generous with small gifts, echoes, refocusings, engineered adjoints on quiet stages. It is stringent with large requests, global unwinding, erasure of deep records, inversion of histories that have branched through many channels. In that light, the meaningful project is not to cajole yesterday into returning, but to decide which records to make resilient and which flows to steer. You can hear that decision in technologies we already use. Error-correcting codes do not prevent noise, they route it into syndromes you can recognize and fix. Archives do not stop decay, they slow it and add redundancy so that losses are rare. Feedback control does not suspend thermodynamics, it buys sharper distributions at a measured cost. Biochemistry does not cheat stochasticity, it spends ATP to proofread and repair. In each case, the arrow is acknowledged and managed rather than denied. Reversal, when it is real, is local and purposeful. Undo that error, refocus that wave, restore that coherence, rewind that specific evolution by carrying the adjoint in your pocket. If one still wants a philosophy of time from these details, it might be this. Becoming is the appearance of new records under constraints that favor their persistence. The future is the direction in which those records accumulate with less effort than would be required to erase them. The dream of reversing time is a yearning to save more than the default drift allows. Physics does not forbid the yearning. It translates it into designs, budgets, and tolerances. On the scales where we live, that translation is already generous. It lets memory endure, instruments refocus, and fragile structures last long enough to matter. On grander scales, it counsels humility. There are further chambers we could still open without treading the same ground. The renormalization of noise in multi-scale systems, where effective dynamics gain memory and non-Markovian arrows at coarse resolution. Gravitational wave tails and memory in cosmological backgrounds. Thermodynamic speed limits for population games and evolutionary search. And the information geometry of quantum clocks, which degrade as they tick and thus spend a resource, coherence, to mark duration. Each would sharpen the same answer by tracing a new boundary between what can be made to return and what must be let go. If you want to continue, we can walk through any of these, keeping the balance between exact statements and the meanings they carry. There is a precise way to watch irreversibility emerge when you discard variables. Start with the equations for a closed, many-body system and apply the projection operator method. Separate the coordinates you care about from the ones you'll treat as an environment. The result is a generalized Langevin equation in which your chosen variables feel a friction term with memory and a noise term with correlations set by the same kernel. This is the Maury-Zwanzig picture. The coarse variables remember what you threw away through a convolution in time, and the fluctuation-dissipation relation links the memory kernel to the noise spectrum. If you were to reverse the flow, you would have to invert that convolution and supply the precise noise realization that occurred. In effect, you would need to recreate the very fluctuations you treated as external. The equations do not forbid it. They reveal exactly which information must be returned to the system for the movie to run backward. The influence functional approach says the same thing in a different dialect. Integrate out the environment's degrees of freedom in a path integral description, and you obtain a non-local functional that modifies the system's action. The real part encodes dissipation. The imaginary part encodes noise. On a closed time contour, the Schwinger-Keldysh formalism, the causal structure is explicit. Fields on the forward and backward branches interact with kernels that vanish outside the light cone and that carry the memory of initial correlations. If you want to engineer a reversal, you must supply boundary conditions and counter kernels that cancel the influence you just computed. The formal steps are perfectly reversible. The operational burden is to enact the exact non-local counter terms with finite accuracy, while nothing else couples to your system. Cosmology provides a stage where the same logic plays out at the largest scales. Gravitational waves propagating on an expanding background accumulate subtle tail contributions because they scatter from the curvature of space-time itself. Memory effects carry through an expanding universe, but their amplitude and angular structure are redshifted and lensed by large-scale structure. In principle, one could compose incoming fields on the cosmological horizon to cancel an astrophysical memory step inside our patch, but the phases would have to be arranged across an expanding sky, partitioned by billions of years of evolution. The arrow is not in the Einstein equations. It is in the boundary dataset by our cosmic history. What remains, in practice, is that detectors on Earth record permanent offsets after violent events, while nothing in the sky delivers the conspiratorial advanced wave that would undo them. Evolutionary dynamics adds a different kind of speed limit. Populations climb rugged fitness landscapes by mutation and selection, a process that can be cast as stochastic dynamics with drift, selection, and diffusion, mutation and drift. There are bounds that relate the rate at which a population's distribution approaches a target to the entropy produced in the process. Fitness flux theorems tie cumulative selective advantage to Kullback Leibler divergences between forward and neutral trajectories. Thermodynamic uncertainty relations adapted to birth-death processes constrain the precision of lineage growth estimates by the dissipated free energy per generation. If you ask to reverse an adaptation, to return a population to an earlier genotype distribution, you face the same inequalities with signs flipped. To do it quickly and reliably, you must pay in resources, narrow controlled bottlenecks, artificial selection, chemostats, that dissipate more than the original episode you're trying to undo. The arrow in evolution is the accumulation of information about the environment. Reversal is a costly de-learning. Timekeeping itself has a resource ledger. An ideal clock is a system whose state evolves with a stable phase that can be read out without destroying it. In quantum theory, the variance of energy bounds how fast a state can move through its space. The quantum Fisher information quantifies the best attainable precision in estimating elapsed time. Autonomous clocks, devices that tick without external control, operate by converting free energy into ordered temporal correlations at an output register. Each tick consumes coherence or chemical potential and generates entropy in a dump. Phase diffusion broadens the tick distribution. Stabilizing it requires feedback or larger energy variance, both of which increase dissipation. There are lower bounds on entropy production per tick and on power precision trade-offs. Reversal here would mean unticking, erasing the temporal record while recovering the work spent to produce it. The inequalities forbid perfection at finite power. Clocks age because precision must be fed. In mesoscopic transport, currents carry another signature of direction. Electrons traversing a nanojunction obey stochastic statistics that can be measured one electron at a time. Full counting statistics record the distribution of transferred charge over a window, and a fluctuation symmetry relates the likelihood of a given current to the likelihood of the opposite current under reversed biases. Onsager reciprocity holds near equilibrium, reflecting micro-reversibility. Magnetic fields, or time-dependent drives, can break it and steer transport asymmetrically. Launder-Budaker theory relates conductance to transmission probabilities. Entropy production is proportional to the product of current and affinity. To reverse a current without changing the affinity requires feedback that measures microscopic states and gates channels conditionally, paying the same information dissipation bills already tallied in other contexts. There is a quiet geometric order in how many irreversible equations approach equilibrium. Fokker-Planck dynamics for diffusive systems can be written as a gradient flow of free energy in a space of probability distributions equipped with a metric, the Wasserstein geometry. The free energy decreases along geodesics. Relative entropy contracts under the semigroup generated by the dynamics. Hypocoercivity extends this picture to kinetic equations that mix conservative transport with dissipative collisions, proving exponential approach to equilibrium even when diffusion acts only in velocity space. Interpreted this way, irreversibility is descent along a curved landscape. Reversing Keim would mean climbing back up gradients against the geometry. You can do it if you inject work to drive the system along a controlled path. You cannot do it by fiat within the autonomous flow. A different mathematical arrow lies in analytic continuation. Imaginary time correlation functions in quantum many-body systems are easier to compute by Monte Carlo than real-time responses, but the inverse map from imaginary time data to real frequency spectra is an ill-posed inversion akin to running diffusion backward. The kernel that connects them exponentially damps high-frequency features. Recovering a spectrum demands priors and regularization, maximum entropy methods, Bayesian inference, which effectively supply information the forward transformation has buried. The failure to invert cleanly is not about microphysics. It is about the structure of integral transforms that smear detail. In a literal sense, many inverse problems are small models of time reversal. To go back, you must declare what kinds of originals you consider plausible. Signals in disordered media tell the same story with different instruments. A wave launched into a random waveguide experiences multiple scattering. The transmitted field, recorded over frequency and channel, encodes a complicated transfer matrix. Singular value decompositions reveal modes that transmit well and modes that are trapped. Shaping an input to excite the bright modes delivers energy efficiently. Shaping it to excite the time-reversed response of a desired focus reconstructs a spot deep in the medium. But this success rests on having measured the matrix recently. The medium ages as scatterers drift, and the inverse becomes stale. Reversal fades as decorrelation grows. Practical schemes introduce continual relearning, paying bandwidth and power to keep the inverse matched to a changing world. Coarsening dynamics in phase-separating mixtures furnish another asymmetric script. After a quench, domains of the two phases grow as interfaces move to reduce curvature-driven energy. The characteristic length scale increases as a power of time set by the mechanism: diffusive transport, viscous hydrodynamics, or inertial flow. The scaling forms are self-similar. The statistics of domain shapes collapse when rescaled by the growing length scale. Attempting reversal would mean reconstructing the intricate interfacial geometry at an earlier time and then stabilizing it against curvature flow. In practice, any attempt to rebuild the earlier mosaic triggers the same dynamics that erase it, unless one applies spatially patterned fields that supply curvature with the opposite sign. Like anti-diffusion, anti-coarsening is well defined in equations only when you add terms that inject energy and information in lockstep with the growth you are unwinding. There is a conceptual cousin of the time arrow in causality constraints that appear as analyticity in response functions. Kramer's chronic relations connect the real and imaginary parts of a linear response by integrals that assume no signals arrive before their causes. The assumption is not negotiable data fitting. It is a statement about analyticity in the upper half of the complex frequency plane, grounded in causality. Violations would permit acausal behavior. If one dreams of reversal that sends influences upstream, these dispersion relations mark the walls. Any effective medium that appears to do so must hide the costs in gain, noise, or bandwidth limitations that keep analyticity intact. Noise itself renormalizes as you change scale. In multi-scale systems with slow and fast variables, eliminating the fast ones often leaves the slow dynamics with colored noise and memory. The effective equations can acquire non-Markovian kernels even when the microphysics laws are Markovian. This emergent memory creates arrows at the coarse level that are invisible in the fine description. It also sets traps for naive inversion, fitting a Markovian model to data generated by a hidden, non-Markovian process produces apparent time asymmetries and prediction retrodiction gaps that are artifacts of misspecified models. Properly acknowledging memory leads back to the generalized Langevin picture, where reversing means inverting kernels you were tempted to ignore. In active systems that learn from streams, there are fundamental inequalities linking improvement to cost. A controller that updates parameters theta to reduce predictive loss follows a stochastic differential equation on a statistical manifold. The expected drop in loss per unit time is bounded by the product of a learning rate and the Fisher information metric, while the entropy exported to a thermal environment lower bounds the integrated squared speed in that metric.
These bounds become design constraints. To back out a parameter update without paying the cost again, you would need to reverse both the physical changes in memory and the information flow with the environment. Even if the abstract optimization is formally reversible, the embodiment is not, for the same reasons that computation without erasure is a limit case requiring infinite slowness and exact isolation. There is also a subtle arrow in record statistics, the mathematics of new highs and lows in noisy processes. For independent, identically distributed draws, the expected number of records up to time n grows like the harmonic series, with the rate of new records decaying as 1 over n. In correlated processes, like random walks with drift, asymmetries appear. Positive drift increases record rates in one direction and suppresses them in the other. If records stand in from memories written into a system, this mathematics predicts a forward asymmetry in how often fresh records appear versus how often old records are erased by large excursions in the opposite direction. Reversal would mean flipping the drift or changing the noise law, altering the process rather than rerunning it. Finally, one can step back and consider a composite picture that respects both the romance and the restraint of the problem. Equations at the micro level are mostly symmetric under time reversal. Arrows arise from boundary conditions, coarse graining, and the combinatorics of many degrees of freedom. Every credible scheme for reverse requires one of two strategies. Either isolate a small enough subsystem that you can compute and apply the exact adjoint dynamics with tolerable error, or broaden the system to include controllers and baths that pay the entropic debt while you sculpt a local unwinding. The first strategy yields echoes, refocusings, and engineered backtracks. The second yields refrigeration, error correction, and learning that can be undone only by spending again what was spent. If there is a philosophy to carry away, it is not that time is a tyrant, but that it is an accountant. The ledger is clear. Information dispersed must be recollected. Correlations forgotten must be repurchased. Gradients spent must be rebuilt. Physics does not extinguish the dream of reversal. It prices it. In small rooms with quiet walls, the prices are low, and the miracles ordinary. In large rooms open to the sky, the prices soar, and the shop is closed by the time the bill arrives. Between these, most of life happens, repairing what can be repaired, preserving what can be preserved, and letting the rest become part of the deep record that points, with remarkable consistency, the way we call forward. We set out with a bold question, and arrived somewhere quieter where answers take the shape of responsibilities. Along the way, we learned that the equations we trust are almost perfectly symmetric. That at small scales, they permit a graceful reversal when we know enough and disturb little. We also learned why those graces do not scale. Information leaks, correlations disperse, boundary conditions choose, costs accrue. The arrow we live under is not a tyrant, but an accountant, and its ledgers are thorough. When many degrees of freedom are involved, the price of unhappening dwarfs any resource an agent could gather, and so the grand dream of running the world backward recedes into the distance like a mirage that keeps its beauty by staying just out of reach. That distance does not make the journey empty. It clarifies what is possible, and more importantly, what is worth doing. In small rooms with quiet walls, we can make echoes return. We can ask waves to fold themselves back to a point. We can guide spins into harmony after they drift. We can construct the adjoint of a carefully known evolution and watch a quantum state step home again. These are not party tricks. They are demonstrations that the world, in principle, remembers, and that memory can be coaxed into the open when we carry enough knowledge to match it and enough patience to protect it. Such moments are not defiance of the arrow, they are local treaties with it, agreements that allow a small reversal in exchange for careful isolation, accurate control, and a willingness to pay in energy and attention. What we call time's flow turned out to be a tapestry woven from many strands. Thermodynamic drift, radiative boundary conditions, the geometry of space-time, the coarse grainings we adopt, the limits of our control, and the rarity of conspiratorial initial states, each contributes to the one-way feel.
It is tempting to imagine that a single master switch could flip all of these at once, but that hope misunderstands their nature. The strands are not independent laws waiting for a command, they are consequences that arise together because the world is large and you and I are small. Reverse one strand and the others tug it back into place. Even when the equations admit advanced waves that gather themselves toward a charge or a gravitational memory that could be canceled by incoming fields from the edge of the universe, the boundary data required are so extreme, so delicately coordinated, that they are absent from the skies we actually inhabit. The discoveries that brought us here did not scold us for asking. They taught us how to ask better. If reversal means rebuilding the correlations that the forward story spread across too many actors, then perhaps the wiser project is to write correlations that matter in forms that travel well. Error-correcting codes are like that. They trade space for time, redundancy for resilience, packing meaning into patterns that can survive noise and be restored from partial traces. Archives and fossils are like that too. They transcribe knowledge into media that fade more slowly than the voices that spoke it. Laboratories are like that when they are well designed. They isolate, stabilize, and document so that the same delicate choreography can be repeated, not because time ran backward, but because the experiment's path was made robust against the nudges that would have sent it wandering elsewhere. There is a different kind of peace available when we accept that some erasures are final. Acceptance is not detachment. It is the moment you stop spending energy on what physics will not sell you and start spending it where the ledger says you can make a difference. The second law does not forbid islands of decreasing entropy. It demands that the sea rise faster than any island sinks. Our lives are built on that allowance. We feed and repair, we learn and teach, we garden and archive, we build thresholds that steer flows rather than deny them. In this, reversal becomes a craft, not a miracle. Restore this fragile pattern, reconstruct this signal, rephase this chorus, retrieve this message from the noise and write it again, clearer than before. Each act is small and local, yet none of them are trivial. They are how meaning survives in a universe that is both generous and unhurried. The science we leaned on was exact where it mattered. It showed why erasure has a cost, why clocks spend coherence to tick, why feedback can sharpen distributions only by paying thermodynamic dues, why computation without heat is a limit that asks you to go infinitely slow and never forget. It showed why turbulence cascades energy one way, why critical points hold history like amber, why active matter marches to built-in arrows, why renormalization flows encode a loss of ultraviolet detail that no infrared theory can perfectly restore. Every calculation kept circling back to the same gentle truth. To run backward, you must bring information the forward flow discarded, and you must carry that information in a physical form. Bits that are written, protected, and eventually reset. The price is not a metaphor, it is a sum in joules. Yet, the story would be incomplete if we spoke only of costs. The same ledger that prices reversal also values care. When you measure with less disturbance, when you design protocols that follow geometric geodesics and waste little, when you encode so that a fault becomes a correctable syndrome rather than a catastrophe, you are bending the local arrow as far as fairness allows. These are acts of conservation in the deepest sense. They take the long view without pretending to own the river. They make room for memory and return within a universe that will not trade its boundary conditions away. Perhaps that is the philosophical center we can carry out of this room. Time is not just a parameter, it is the habit the world has of writing its own record. The future is the direction in which those records accumulate with less effort than erasing them would require. To ask for reversal is to ask for amnesty from that habit. Sometimes amnesty is granted in miniature, an echo forgiven, a wave untangled, a path in Hilbert space walked back with care. Most often, the amnesty we are offered is constructive. Build structures that remember longer. Learn to measure without unmaking. Choose descriptions that keep what must be kept, and let the rest pass without bitterness. That is neither resignation nor consolation prize. It is the dignity of living with laws that do not bend for us, but do reward our understanding. There is also a moral in the shape of our initial conditions. The cosmological arrow begins in a smoothness we did not choose. We inherited a universe where free energy is available to write records, to build stars and cells and songs, and to maintain pockets of order against fluctuations that would otherwise erase them. It is a remarkable inheritance. The very asymmetry that prevents global reversal is the one that permits life. To wish it gone is to wish our stage away. Better, then, to treat the asymmetry as a gift that asks for stewardship. Use it to keep promises. Use it to rescue signals. Use it to form communities where knowledge crosses generations without fraying into rumor. Use it to leave the next travelers more structure than you received, not because time can be made to walk backward, but because meaning can be made to last longer. When we began, the question glowed with romance. Could we reverse the flow of time? The answer we found is gentler than yes or no. On the scales that measure lives, no. On the scales that measure experiments and instruments, sometimes. On the scale of the universe, not by any lever available to beings within it. What remains, and it is more than enough, is the practice of return. Return a system to coherence long enough to learn from it. Return a message to clarity after noise has clouded it. Return to the same question with better tools and see the same landscape with sharper eyes. Return to the work of keeping, repairing, and transmitting, because that work is what our kind of creature does best. So, let the river run. Learn its eddies. Chart the shelves where currents slow, and build harbors where vessels can be mended without pretending that the tide will stop. Accept that some things are carried out to sea and will not be seen again. But do not mistake acceptance for surrender. Carry your knowledge like a lantern and use it to help small patterns endure. The glint of a result that might otherwise be lost, the integrity of a memory that might otherwise fade, the coherence of a song that might otherwise be drowned by noise. And that, in a universe that balances its books with such unwavering care, is a kind of grace. Good night, time traveler. We will meet in our next exploration.